Okay, after some technical difficulties, here we go. Now, like I said, there are 21 people here, so for the rest of you, some of you informed me that you could not be here today, so thank you for doing that. And the rest of you who apparently decided to change this class from Monday, Wednesday, Friday class into a Monday, Wednesday class, y'all suck. Seriously, that is not a recipe for success. Okay, so this week, so then we're going to wrap up what we're covering all week. Inhomogeneous equations. Variation of parameters. This is 3.6 in the text, 3.7 in the notes. I think after this point, or after this chapter, the sections and notes in the text will be aligned. Now, starting from the general form of a solution, so this second order for the e, y double prime plus any coefficient p of t y prime plus q of t y equals some g of t. Has this form. So we have y sub h, which is a solution of the corresponding homogeneous equation. So plus a particular solution. And recall that this is, plus you, abbreviated as Ly is equal to G. So this is a homogeneous solution, therefore the solution of Ly equals 0, and this solves Ly equals G. And moreover, we can say something about the form of this. So homogeneous solution is a constant, y1 of t plus another constant y2 of t, and then so that's YH. I mean, the particular solution can be written in this form, W1 of t, Y1. So now instead of constants, we have functions. Where Y1, Y2 together make a fundamental set of solutions. In other words, any two linearly independent solutions of the homogeneous equation. Okay. Like your exponentials or like e to the alpha t sine and cosine beta t. And you can think of W1 and W2, since they're not constants, as varying parameters. Parameters that vary with t, as opposed to C1 and C2 that are constants. Also, we have formulas for W1 and W2 that I derived back on Monday. So W1 is the integral of minus G y2 over Vronsky of y1 and y2. And then W2 is similar. There's just no minus sign. And we have y1 up top instead of y2, still dividing by Vronsky. Okay. Now, in the so this is something that always applies for this second order linear non-homogeneous DE. But what we've been focusing on, what we spent time on Wednesday was a special case of this, where if P and Q are constant, then of course we know what y1 and y2 are in all the different cases, and then we know what the Wronskian is. So we can use undetermined coefficients for certain G, the kind of forms of G that I talked about last time, like if G is a polynomial times an exponential, or times a sine or cosine, or a sum of terms of that form. And the reason for that is, in those cases, we can predict what form the integrals, W1 and W2, all worked out, is going to have. So we can just enumerate all the possibilities. But what if we don't have that? What if P and Q are not constant? Or what if G is not of one of those forms? Undetermined coefficients is not going to help us. But this is something we can always fall back on. It's a matter of can we evaluate the integral. So variation of parameters is when is an alternative to undetermined coefficients, where you just go ahead and form these integrals, which are always the case anyway, and just go ahead and evaluate them directly. All right. So for instance, on a test, if I give you a problem where we have a DE like this that does not have constant coefficients, in that case you would not know how to get y1 and y2, so I would have to give you those, and then you work with that y1 and y2 to get w1 and w2. In fact, that's what this example is. Okay, so we have ty double prime minus 1 plus t y prime plus y t squared e to the 2t. Right, and we're not going to bother with initial conditions in this case. But it's important to get this in the right form. Everything I did in the previous board had y double prime plus other things. So y double prime needs to be isolated. So you need to divide by t. So y double prime minus 1 plus t over t, y prime plus 1 over t y is equal to t, e to the 2t. So this is your g that you'll work with in the integrals we're about to do. Okay. So I'm going to give you, I guess for a general problem like this, there are no set techniques for coming up with y1 and y2. There's certain special cases there are. Like in one of the homeworks in this chapter, there's a case where, depending on certain patterns of coefficients, you can find solutions by converting it to a problem with constant coefficients. But if you can't do that, you're kind of up a creek. So in this case, I will give you the solutions. So y1 will be 1 plus t, and y2 will be e to the t. So both of these are solutions. They're obviously not multiples of one another, so they're linearly independent. They make a fundamental set of solutions. So to set up the integrals for w1, w2 that we're going to need, we need a Wronskian. Of course, for Wronskian, we need the derivatives. So 1 and e to the t. So now we can get the Wronskian. Okay, so that is y1, y2 prime minus y2, y1 prime. go ahead and fill all that in. So we have 1 plus t e to the t minus y2 t times 1. And there's going to be some cancellation. So we have, we distribute, we get e to the t appearing here and minus e to the t here. So that and that are going to cancel. And what's left is t e to the t. So that's going to go in our denominator. So now we can go ahead and set up the integrals we need to evaluate. So W1 is the integral of minus g y2 over Wronskian. Okay, so we have g is t e to the 2t, y2 is e to the t, divided by Wronskian, so that's t e to the t. Now what almost always happens in these problems when you set up these integrals, there tends to be a ton of simplification. We see things canceling out all over the place. So we have minus e to the 2t dt. Okay, so what's the integral of that?
1/2 e to the 2t.
Yeah, and then
Negative.
yeah, 1/2 e to the 2t. Now, we could put in a plus c, but it turns out there's no reason to here. It's actually redundant, and the reason for that is if we go back to the general solution that I wrote here. After you work out the integrals for W1, W2, what do? You multiply them by y1 and y2. So if I have a constant, a plus c in here, that's going to multiply y1. But I already have a constant multiplying y1. So you're adding a redundant arbitrary constant. So for purposes of constructing the general solution, you just go with these constants and not include plus c's in here just as a convenience. Because if you're given initial conditions, you'll use these constants to enforce the initial conditions anyway. So I know your Cal 2 instructor always said, always include the plus c. But anyway, it doesn't hurt it, at least. Okay, so that's W1. W2, so we have g y1 over the Wronskian. So we fill in that. So g is t e to the t. 1 plus t is there. And then we have t e to the t for Wronskian also. So again, not a very interesting integral. So we just get 1 plus t. Okay. Nope. Something.
I have a question. Yeah, that should be.
Yeah, it's even 2t. Yeah. Okay. So, all right. So when it simplifies, one of the e to the t's cancels. We're still left the t's cancel. So we just have 1 plus t e to the t. All right. Okay. Well, how would that have to be handled?
Yeah, we use like u times the
Integration
integration of
by parts. I know. Well, first let's break it up into two terms. So we have e to the t plus t e to the t. So at least the first term is easily handled. Okay. So for integration by parts, I'll go ahead and do that up here. What should your u be? T. there's a power of t in there, make that your u, because it's going to keep decreasing until it's all gone. So then dv is just e to the t, dt. So v is just e to the t, and du is just dt. So we have t e to the t minus integral of v du, but that's just e to the t. So we get t minus 1 e to the t. So, so if I fill that in back down here, the minus e to the t will cancel with a plus e to the t over here. So you get t e to the t. So that is your W2. So now we can finally construct the general solution. Actually, I'll do it over here. Oh, man. Apparently nobody who teaches in this building or in this room is like to let the chalk dust accumulate on the eraser. The booby trap class for first person in the morning. So the general solution is first the homogeneous solution. So C1, all right, so C1y1 plus C2y2 plus W1y1 plus W2y2. And now we can fill in the blanks. So C1, C2 remain undetermined. So C1, 1 plus T plus C2 e to the T. And then W1 turned out to be minus 1/2 e to the 2t times 1 plus t. And then W2 turned out to be t e to the t, and then times e to the t. So you can optionally simplify from there. If you were given initial conditions, then y0 is something, y prime is 0 equals something, then you would force them on this. You plug in t equals 0 into the whole thing, and also into the derivative of the whole thing. Okay. So this is an approach you can always take to solving non-homogeneous equations. So if a problem of p and q are constant and g is in the right form, you have a choice. You can apply either undetermined coefficients, or you can do this. I guess it really just depends on how you feel about your integration skills. So, are there any questions about this example? Because there'll certainly be a problem like this on a test where you would not be able to use undetermined coefficients. You'd have to do this, and therefore you'd also have to be given y1 and y2. All right. Now let's take a look at another. Okay. Now this is sort of a problem where you can use either method. Y double prime minus 2y prime plus y is equal to 2e to the t. So a problem like this where you have constant coefficients. So here you're not given the y1 and y2. So in order to get the y1 and y2 that you end up needing for everything else, what's the first thing you should do? What? I'm sorry, am I hearing?
Make it a homogeneous equation.
Yeah, so we look at the homogeneous equation. So y double prime minus 2y prime plus y equals 0, and then what?
Find the characteristic.
Yes, characteristic equation, which is?
R squared minus 2r plus 1 equals 0.
Okay, yeah, just replacing orders of differentiation by powers of r. How's this factor? All right, so that is a perfect square. So we have a double root. So r1 and r2 are both equal to 1. So therefore, what are your y1 and y2? Sorry, what?
C1 e to the power d.
Yeah, well, we'll do the constants now, but yeah, just the y1 and y2. Yes, y1 is e to the t, and y2 plus. We need a t e to the t because of the double root. Okay. So then, if we have constant times y1 plus constant times y2, that's a general solution of the homogeneous equation. But now we can use these to find w1 and w2 for our particular solution. Okay. So next we need the w1 and w2t for a particular solution, yp to t. So based on what I've shown you so far, what's the next thing we should do? We need a derivatives. Okay, so y1 prime is just e to t. What about y2 prime?
E to the t plus t.
Yeah, using product rule, so e to t from differentiating this, and then plus t e to the t from differentiating the exponential. Okay, and what do we do with those? Wronskian, yeah. So okay, so that's y1, y2 prime minus y2, y1 prime. So we have e to the t plus t e to the t minus y2 t e to the t times y1, which is e to the t. What is that going to simplify to?
E to the 2t.
Yeah, because we have t e to the 2t over here, and then when you distribute the e to the t from here, we get this minus. So we have plus t e to the 2t. So that's going to cancel, and that's going to cancel, leaving only e to the 2t. So that is our Wronskian. Okay. And now what do we do? Based on the last example.
Solve for w1 and w2.
All right, so, okay, so what's our formula for W1 give us? Just putting the pieces together.
Negative g of t.
Yeah, and G is
2e to the t.
2e to the t times what? The y2, which is t e to the t, over
E to the 2t.
Wronskian. Yeah, e to the 2t. Okay, and then once we simplify everything that we can, what's left?
2t.
Yeah.
Minus
So
2t.
the integrals are, yes, minus 2t. So thankfully, you always end up with less interesting integrals than what you started with. Okay, so what do we end up with?
Negative t squared.
Minus t squared. Okay, so that's our W1. And then for W2, so putting the pieces in.
2e to the t.
Yeah, so our G,
E to the t.
e to the t, which is G y1 over Wronskian, which simplifies to,
2.
yeah, so that worked out pretty nicely. Okay. All right. So now, when it's time to write down the general solution, it's in all the pieces that are all somewhere in the board, all we have. Mm-hmm. C1 e to the t.
Let's say 2t to the et.
Yeah, so this is our y1, and this is our y2, okay? Plus,
Negative t squared.
E to the t.
yeah, times e to the t. So we have w1, y1, okay?
Plus 2t.
T.
T e to the t.
Yeah, e to the t. So w2, y2. Okay. Okay, so and at this point, like for instance, if this was a test, you could stop. Well, in the case where there are no initial conditions, because I would not require you to simplify this. But I'm going to make up some initial conditions. I'll say y0 equals 1, y prime of 0 is minus 1, so it's like pretty generic. And if you get initial conditions to satisfy, what I would recommend is you see if you can simplify this. What can this simplify?
The last two terms can simplify just to 1.
Yeah, because you have a minus t squared e to the t, and then these combine to give a 2t squared e to the t. So you get, so instead of 4 terms, you only have 3. T e to the t plus t squared e to the t. So it's like you have a quadratic function times e to the t, where two of the coefficients, the linear constant ones, are not determined, only the quadratic one is. So it's not really surprising that this can happen, because your integral for W1 includes y2, which if it's an exponential, the exponential is going to be there. And then you're multiplying it by y1, and then vice versa for the other one. A plus also there's a minus in there. So it's not uncommon to have, especially when there's exponentials involved, both multiplied together in each term of your particular solution. So always look for this opportunity to make life easier for this last step. So we have these initial conditions. I need to evaluate y of 0. So if I plug in 0 here, what am I going to get?
C1.
Yeah, all the other terms are going to go away, so that worked out nicely. And that must be equal to 1. So C1 is now determined. So now there's only one coefficient left. And then we need the derivative. Well, for first term, this is just going to be e to the t. And then for rest, unfortunately, the product rule is needed. Okay, so what's the product rule going to give us for the next term?
E to the t plus t e to the t.
And finally, for the last term,
Two t e to the t plus t squared e to the t.
yeah, okay. But now you plug in t equals 0. Much of this is going to go away. So what's going to be left?
C2.
Yeah, because that are all going to go away when you plug in t equals 0. Okay, and that must be equal to minus 1. So C2 is minus 2. Okay, so now we can write down the final solution. So y of t is e to the t minus 2t e to the t plus t squared e to the t. All right. So for full-blown initial value problem, this is non-homogeneous. This is how you could solve it. So the interesting part of this really is what are the integrals? How difficult is it to work them out?
And you said the initial conditions only on the test for this type of problem?
It can be.
Oh,
Yeah. Yeah, it's so on the test, you're going to definitely see certain types of problems. Like, okay, for homogeneous case, actually, I have 10 minutes, so I'll go ahead and write that down. What we've seen so far, that is going to be in the test. So write the different types of equations, and for some of these I'll put additional conditions, and some of these I won't. It's all on a whim. So if they're not, you're just writing down the general solution. In other words, you could stop here if there are no initial conditions given. Okay. And again, it's better not to simplify in that case. Okay, so types of equations. Now, all of the equations fall into this category of second order and linear. Then let's break that down a little further. We have homogeneous and constant coefficients. And that breaks down into a few categories. So we have, so in all these cases, you're going to find your characteristic equation and get the two roots. So we have distinct real roots. So that leads to y1, y2 being e to the lambda 1t, e to the lambda 2t. Then we have complex roots. So that's going to lead you to e to the alpha t cosine beta t, e to the alpha t sine beta t, where your complex roots are alpha plus or minus I beta, whereas in the first case, your real roots are lambda 1, lambda 2. And finally, repeated roots. So we just have lambda and lambda, so that leads to e to the lambda t, t e to the lambda t for your y1 and y2. Okay, so you'll definitely have a problem with each of those. So be really careful in computing your roots, then you'll know what lies ahead. Let's go from one problem to the next. Also, in under a still homogeneous, but not necessarily constant coefficient, there's reduction of order. Now we use that to derive the second solution in a repeated root case, but so given y1, use the reduction of order technique to find y2. So that would be for a problem that does not have constant coefficients, so you wouldn't know how to get y1 and y2 otherwise. Okay. And then we have non-homogeneous. And that's going to be, so we have a g of t, and if it is constant coefficients, then generally you can use the method of undetermined coefficients. And then, if they're not constant, then that's when you would use, you have no choice but to use variation of parameter that you've seen today. It's allergy season. In that case, like in the first example today, they'd be given y1, y2 for that. And the last bit of room I have on the board, the only thing on a test that has not been covered yet, so mechanical vibrations. Which is an application of certain second order DE with constant coefficients, where we're looking at like a mass on a spring, and the solution describes the motion of a mass over time. Is it going to oscillate forever, or if there's damping, will the oscillation die down over time? So this is okay. So in the text, this is 3.1 to 3.4. Reduction of order is also 3.4. Non-homogeneous stuff is 3.5 and 6. Sections may be slightly different in the notes, but the sections would have the same names. And then 3.7 is a mechanical vibration. So Dr. Zhu is going to start covering that on Monday when I'm not here. And then depending on how far he gets, I may continue with that on Wednesday. And that'll be it for the chapter. So then we'll have a couple class periods to do some review or some practice like we did, like the simulations, to help you get your speed up. And then the test will be, 2 weeks from last Wednesday. So, okay. So, see you Wednesday.